Welcome back to Project Pulse. In the previous lessons, we looked at the initial CapEx it takes to develop and build our battery project. In this session, we are moving one step further along the life cycle. We will tackle the continued CapEx that is required to keep the asset performing, more specifically, the augmentation events. On the cash flow waterfall, you can see two green blocks. That's the MMRA, or also referred to as Major Maintenance Reserve Account. In this lesson, we will model both the augmentation CapEx and the Major Maintenance Reserve Account that funds it. If you're new to this Deal Lab series, I recommend starting with part 1, where you can download the model start file for free and build the model alongside me. Link is in the video description below. And the information memorandum for this case study gives us everything we need for this lesson. Down at the bottom are the augmentation parameters. And you can see the unit cost in US dollar per kilowatt hour, the maximum number of augmentations over the asset life, and the target to maintain contracted AC capacity at the point of interconnection over 20 years. And on the right, the Major Maintenance Reserve Account parameters tell us how the reserve works. Purpose is to pre-fund battery augmentations, funding comes from cash flow from operations, and the target build-up is around 3 to 4 years before each augmentation event, depending on the size of that augmentation. Now let's move back to the checkpoint file from our previous lesson. All of these assumptions are already translated into the inputs time independent sheet. Something to note here is that different cases assume different cycling patterns and degradation speeds. Some cases have less cycling and lower degradation, others assume more aggressive cycling and faster degradation. For example, in case 1, we only need about a 15% buffer increase to restore enough headroom above the minimum nameplate threshold. And in our currently selected fully merchant case, case 15, we assume a 30% capacity headroom increase over 2 augmentation events. And the trigger settings in row 235 make sure that each augmentation is scheduled before the usable capacity would fall below the minimum threshold. So we upgrade the battery just in time, not too early and not too late. And finally, the build-up period in this case study is 3 to 4 years before each augmentation, depending on how large that augmentation campaign is. Now let's move to the operations sheet and turn these assumptions into the model logic. To model augmentation CapEx, we basically need 3 ingredients. First, we need the timing of each augmentation event, which we already determined on the energy and power side of the model in our previous lessons. And second, the unit cost per installed DC energy, here in US dollars per kilowatt hour, including any inflation-adjusted price change over time. In this case, we are actually assuming cost deflation, so later augmentations get cheaper in real terms. And the last thing we will need to model our augmentation CapEx is the amount of energy we need to restore at each event. That's the kilowatt hours DC we add back to bring the system back up to the target capacity and duration. Alright, with that background, now let's get to the actual modeling side. We will start by pulling in our augmentation flags, which is basically the timing of each augmentation event, which we have already modeled in one of our first lessons. So we'll pull in the flags for augmentation 1, which is modeled in row 72, and for augmentation 2, which is modeled in row 80. So let's remember 72 and 80. Scroll back down. And here we can simply refer to K72 as well as K80. Drag this one over, Control R. And you can see that for case 15, which is our fully merchant case, our first augmentation will be scheduled in 2033. And then we would have a second one in 2041. And the case study is saying that we want a maximum of 2 augmentations over the asset life. And that is directly related to the inputs we choose right here for our percent buffer increase, which is in row 232. For example, if you would reduce this to 10%, we would get a fail and a nameplate breach check. because we would already require an augmentation in 2033, then again in 2037. And if you scroll up to the power and energy section, you would see that we would breach our nameplate capacity in year 2040, and we could essentially not maintain our minimum nameplate capacity. So that's the reason why all of these inputs here are basically sized so that we only need a maximum of 2 augmentation events. So let's restore this to 30%, go back to the operations sheet, and scroll down to the augmentation CapEx section. And then we can pull in the augmentation capital expenditures on a real basis in row 364. And that is going to be our augmentation 1 flag. So the first flag here. And we'll multiply this with our input that we're given right here. So we need to restore 65,000 kilowatt hours on a DC basis. Hit F4 1, 2, 3 times. That gives us the energy. And the cost on a per unit basis is given in H364. Hit F4 once. So it costs $200 per kilowatt hour DC on real 2025 terms, so before any inflation adjustment. And since this is given in USD, we will have to divide by 1,000 because our unit for the actual rows is thousands USD. Hit enter, drag this over, Control R. And you can see that before any inflation adjustment, we would assume the augmentation to cost about $13.1 million in year 2033. Then we can copy this formula, hit Alt HVSF, so we maintain our formatting, hit enter and drag it over for the second row. Make sure you got the anchoring right, so hit F2, make sure all of these references are correct. And it appears they are, so that's great. Hit enter. Then we can calculate our total augmentation CapEx. That's basically just the sum of these 2 rows. Drag this one over, Control R. And then we actually assume an augmentation index, which is fairly industry norm. So if you scroll up to our inflation assumptions, you will see that for the augmentation, we have a deflationary index, meaning we expect that the costs of the batteries in the future will decrease. That's a macroeconomic assumption you will have to make when modeling the project, but in this case study we assume that the batteries get cheaper in the future. So what we'll do is to take our first augmentation cost on a real basis, so K364, and multiply this with an X lookup. The lookup value, as per usual, is our escalation selection right here. Hit F4 once, comma, and then we can scroll up all the way to our indexation assumptions. Select this list here, hit F4 once to fully anchor it, and the return array should be this one here. And here we hit F4 1, 2 times to only anchor it to our row. If not found, that's a 0. Match mode is exact. So 2 zeros, close parentheses, hit enter. Let's copy this, hit Alt HVSF to paste special formulas, drag this over, Control R. And you see that our initially anticipated $13.1 million in real terms today are now actually just 11.5 million in year 2033 and 11.3 million in year 2041. So let's take the sum of these 2 up here, drag it over, Control R. And after inflation adjustments, we essentially now only expect 22.8 million versus 26.3 million in costs. Now you might have noticed that we get a fail again in our checks. So let's move to our checks. And that comes from our balance sheet. Let's move to our balance sheet. And you can see that there's going to be a mismatch once the augmentation kicks in. And that can indeed be expected because right now we have only partially implemented our augmentation. What's missing is our MMRA, which will offset these costs. So let's go back to the operations sheet. And now that we know what it will cost to fully augment our batteries, let's move on to our major maintenance reserve account. So for background, lenders and usually also equity sponsors want to make sure that these major replacements do not require fresh capital injections when they occur. Since 11.5 and 11.3 million USD is quite a significant expense, we want to implement a major maintenance reserve account. And what a major maintenance reserve account basically does is divert a portion of the operating cash flow into a reserve account in the years leading up to each augmentation. And this balance then accumulates as restricted cash, and when the augmentation happens, the MMRA is drawn down to pay for the CapEx. And the first thing we will implement is our augmentation flags or MMRA build-up flags. And that's basically the moment when we will start collecting operating cash flow to save up for our augmentation expense. And that should happen 4 years prior to the actual augmentation. And to do this, we will use a if sum and offset combination. So type if the sum, and our sum will start with our first augmentation flag up here, K360, colon, so we referred from K360 to, and then we will offset. We will actually offset K360 by comma 0 rows. So let's just do 2 commas. And what we want to offset it by is a certain amount of columns. And that is given here in G375, which we will fully anchor. And since we only want to start saving money 4 years prior, so what the offset function does as it's modeled right now, it would count this cell right here and 4 future references, which would be 1 too many, which is the reason why we subtract 1 from G375, close parentheses 1 2 times. And if this is not equal to 0, so smaller or greater than 0, or basically just 1 because we have a flag, then we want a 1 to be returned because then our flag here turns on, otherwise 0, close parentheses, and hit enter. Let's see if that worked. Control R. And you can see that now here we start saving in 2030 because this reference is offset by 1 to 3 years. And I can demonstrate what would happen if we take out the -1 right here. If you drag this one over, Control R, actually copy and paste this here, you would see that we would start saving 1 year too early. So let's make sure that we get the formula right. Control R and actually just subtract 1. So we start saving 4 years in advance of our actual augmentation event, which is, from a financial modeling standpoint, assumed to occur at the year end, so on the 31st of December, which means we start saving up on the 1st of January until the 31st of December 2033. Then let's copy this flag, paste it here for our second augmentation, Control R, and you can see the same goes for our second augmentation. Now that we know when our MMRA should start building up, we can now model the contributions. And that is going to be equal to our actual cost, which we have modeled in 369. And here we will refer to the sum of the total cost. So let's just refer to J369, because in other cases, our actual augmentation expense might not occur in the same year. So we always want to refer to the total sum or row sum. Hit F4 1, 2, 3 times to only anchor it to the column, so it can move down in rows for our second formula here. And we'll multiply this with our augmentation 1 flag. And we will then have to divide this by our actual build-up period, which is 4 years, because otherwise we just contribute 4 times this amount, which would certainly be too much. So make sure that we also divide this by our actual build up, and even better practice would be to take the row sum here as well. So let's actually just refer to J375 and hit F4 1, 2, 3 times. enter, copy this, Alt H VSF to paste special formulas, and let's drag this one over, Control R. And you can see that now we built up $2.8 million for 4 years, and the same goes for the period before the second augmentation. So that seems to work great. We can take the sum of these two rows here, drag it over, Control R, and that will allow us to now model our major maintenance reserve account, which will then also sit in our balance sheet. So as always, for an account for the balance brought forward, we refer to the previous balance carried forward. So this is the reason why this cell style here is empty, to make sure that no one puts in any value right here. Then right here, this is the sum of these 3 cells above. Hit enter. And for the MMRA contributions, we can simply link to our total row here in 381. And for our release, we want to make sure that this is a negative number now. So minus our actual total augmentation CapEx on a nominal basis. So K371. Drag all of these ones over, Control R. And you can see that our major maintenance reserve account builds up for 4 years. And within 2033, we will take 11.5 million from our operating cash flow and then distribute it simultaneously to make sure that we have enough cash to pay for augmentation. Now let's move to our integrated financial statements and see how this is implemented right here. And you can see that once we start in our cash flow statement, after our revenue and OPEX, we take out our MMRA contributions, which reduces our operating cash flow. And you can see that actually right here, the actual expense would be in 2033, 11.5 million. And the operating cash flow in that year is actually just $11 million, which means that without an MMRA, we would actually not have enough cash. So that's why we spread out this cost over a period of 4 years. So each year our operating cash flow is reduced, and that will give us our CFETs, which we'll later use to size our debt. And from an investing cash flow perspective, we will then, in the same year where the actual augmentation takes place, have an MMRA release of 11.5 million, which will then be used to actually pay for our augmentation CapEx. So the CFETs from here to our cash flow available for our debt service reserve LC is the same, because we will use our MMRA account balance to pay for the augmentation CapEx. And then once we scroll down further, you can see that we also have a restricted cash account at the bottom of our cash flow statement. So the MMRA basically just builds up as a restricted cash account and doesn't just sit with our regular other cash in the SPV. And since we haven't yet fully modeled all of our depreciation and amortization, as well as our PP&E account and so forth, we still get a balance sheet check. But by the end of this course, if we do everything right, we should hopefully not get a balance sheet check anymore. So what we can do for now is just ignore that fail check. And as we continue working through the next lessons, our balance sheet should start balancing again. And lastly, you can also see the major maintenance reserve account here showing up under our current assets section within the balance sheet. All right, guys, this was it for this lesson, and I will see you in the next lesson. See you there.